This is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to continue the discussion of electrostatic boundary value problems in spherical coordinates. I'll work through 4 different examples today, the first one of which is a problem that you can find in just about any undergraduate electromagnetism textbook, and that is the case of a grounded conducting sphere in an otherwise uniform electric field. So otherwise uniform electric field means that as you get very, very far away from the sphere, the electric field is just going to have some uniform value, E naught, and we have chosen it to point in the z direction. So the first order of business is to write down a general expression for the electrostatic potential. Generally speaking, potential is equal to summation L equals 0 to infinity of A sub L r to the L plus B sub L r to the minus L plus 1 times the Legendre polynomial, alpha order Legendre polynomial. Now, this is my general expression. Now I need to apply the boundary conditions. So what are they? Well, the sphere is grounded, so therefore, V is equal to 0 at the radius of the sphere. It is also true that the potential is equal to 0 everywhere inside. So, why? Because I know the electric field is going to vanish everywhere inside. So, I already know what the interior solution is. I'm just interested in the exterior solution. What are the other boundary conditions do we have? Well, we know that the potential is continuous at the surface of the sphere. We also know there's a discontinuity in the electric field. Discontinuity in the normal component of the electric field at the surface of the sphere is equal to the surface charge density over epsilon naught. And right now that's not going to help us because we don't know what the surface charge density is. You need to figure out the potential some other way. Well, I've got continuity. I know that it's equal to 0 at the radius of the sphere, but what other condition do we have? Well, you're told that the electric field is otherwise uniform. So that means that infinitely far away the electric field is just simply equal to E naught in the z direction, and therefore the potential is not going to vanish, as you might think that, well, the potential has to remain finite as you get very, very far away. You don't want the solution to blow up. However, because there is a uniform electric field, in fact, you will have a non-vanishing contribution from this set of terms because the potential is going to go as minus E naught z, very, very far away. And written in spherical coordinates, that's going to be minus E naught r cosine theta, and that's as r approaches infinity. Okay, so we're just interested in the exterior solution here. What can I get rid of? Well, all of the other coefficients corresponding to the r to the L powers are going to have to vanish because, yes, you don't want your solution to blow up, but you know that the potential is going to go as this. R goes to infinity, these terms are going to go to 0, which is as it should be. So therefore, A sub 1 is equal to minus E naught. Because she'll recall first order Legendre polynomial is equal to cosine theta. So therefore, the first order term here is A sub 1 r to the 1 times p sub 1. So setting those equal to each other as r approaches infinity, just see immediately that A1 is equal to minus E naught. The potential then is equal to the sum of two terms, actually many terms, but we got this term rising from the uniform electric field, and this term, which is basically, if you will, the response of the field to the presence of the conducting sphere. There's a fast way and a long way to proceed from here. I'm going to show you the long way, and I'll show you the short way. The long way involves multiplying through by Legendre polynomials and integrating and making use of the orthogonality condition. And I'm leaving out the arguments here just to give myself a little bit more room. So in other words, if you take the integral from 0 to pi, some Legendre polynomial of the nth order, and some Legendre polynomial of the L primeth order, sine theta, d theta, integrated, what you'll see is that that is equal to 2 times the Kronecker delta of L and L prime over 2L prime plus 1. That means is this interval vanishes unless these subscripts are the same. So in other words, unless L is equal to L prime, this vanishes. What I'll do then is I'm going to make use of the fact that the potential is equal to 0 at the radius of the sphere, because obviously the sphere is grounded, so therefore the potential is 0 there. We have 0 is equal to minus E naught r cosine theta, radius of the sphere cosine theta, plus summation L equals 0 to infinity, p sub L, radius of the sphere minus L plus 1 power times p sub L. And you know, I'm going to rewrite this as P1 here. Okay, so what I'm going to do is I'll multiply through by PL prime sine theta and integrate from 0 to pi. Because of the orthogonality, when I integrate from 0 to pi over the product of the two Legendre polynomials, I'm going to wind up with minus E naught r times 2 Kronecker delta 1 L prime over 2 times 1 plus 1. Second term will have summation L equals 0 to infinity. Radius of the sphere to the minus r, the radius of the sphere to the minus L plus 1 power. Times 2 times the Kronecker delta of L and L prime over 2L plus 1. And because of this Kronecker delta, it doesn't really matter whether you put L or L prime here. It's the same difference. Okay, so what this first term tells you is that L prime is equal to 1. Second term tells you that L is equal to L prime. The effect of the orthogonality condition is that one term out of an infinite number of terms is picked out. Only one term is going to be non-vanishing. So this is equal to B L prime, radius of the sphere minus L prime plus 1, times 2 over 2L prime plus 1. But I know from this first term, L prime also has to be equal to 1. So L prime is equal to L, or L is equal to L prime, and L prime is equal to 1. So you're out of all of these terms, an infinite possible number of terms, you're only going to have one surviving term. This is minus E naught R. And as it turns out, this term or factor is going to cancel out with this one. And therefore the coefficient B sub 1 is equal to E naught R cubed. And that again is the only non-vanishing coefficient from this expansion. Your potential then is equal to minus E naught R cosine theta plus E naught R cubed, radius of the sphere cubed over R squared cosine theta. Some people like to factor out the E naught R cosine theta, and I'll leave you with minus E naught R cosine theta times 1 minus radius of the sphere cubed over the radius of the observation point cubed. And that's your answer. That's the long way. The short way is to recognize from the jump that, well, I still have this orthogonality condition. And the only way that this can vanish at the surface of the sphere, this is equal to P1, is for all other terms to vanish the L equals 1 term, in which case second term just collapses down to B sub 1, P sub 1 over R squared, and then applying the boundary condition that the potential is continuous, you'll wind up with exactly the same solution. This is much faster if you make that, realize that at the beginning of the problem rather than going through and multiplying through by some piece L prime sine theta and integrating from 0 to pi. You just do, well, I know this is cosine theta, so the only way this whole term can vanish for all theta is if all the other coefficients vanish except for the L equals 1 term, which corresponds to B1 cosine theta over R squared. Okay? Now, at the beginning of the problem, I pointed out that you also have another boundary condition which you did not make use of, and that is that the electric field suffers a discontinuity at the surface of the sphere. Electric field vanishes inside surface of the sphere, so therefore our normal component of the exterior solution of the electric field is equal to sigma over epsilon naught, and That means the partial derivative of the exterior potential with respect to the normal evaluated at the surface of the sphere is equal to minus sigma over epsilon naught. Now remember, you get a minus sign here because the electric field is equal to minus the gradient of the potential. And furthermore, rather than writing partial derivative with respect to the normal, I just recognize, well, the normal in this case is pointing in the radial direction, so I'm just taking the partial derivative with respect to r. This is my exterior solution, or rather down here. Therefore, sigma is equal to minus epsilon naught times partial derivative with respect to r, that's minus e naught cosine theta. Second term gives me minus 2 e naught cosine theta r cubed over r cubed. And altogether that's equal to 3 epsilon naught e naught cosine theta. So there's an electric field induced, or rather surface charge density induced on the surface of the sphere due to this external electric field, and that has to be the case because otherwise the electric field would not vanish in the interior as it must in electrostatics. I'll leave this up here for another minute, and then we'll move on. The next problem I'm going to work through is, let's suppose that you have a sphere, and this time you're told what the surface charge density is. Let's suppose that you stick on the surface charge density sigma naught times 3 cosine squared theta minus 1 over 2. And I want to figure out what's the potential everywhere. Both inside and outside. Inside it won't vanish anymore. So if you look at this expression here, you'll see immediately that this is equal to the second order Legendre polynomial. Okay? I'm going to write down the general expression for the potential is equal to summation L equals 0 to infinity. A sub L r to the L plus B sub L r to the minus L plus 1, PL cosine theta. Boundary conditions, well, potential is continuous across the boundary, but there's a discontinuity in the electric field. At the radius of the sphere, that's equal to the surface charge density divided by epsilon naught. And I can write this in terms of the potential it's equal to the partial derivative of the exterior solution with respect to the normal minus partial derivative of the interior solution with respect to the normal is equal to minus sigma over epsilon naught. The reason why we've got this extra minus sign is, of course, because your electric field is equal to minus the gradient of the potential. And since the normal to the surface is in the radial direction, we'll just go ahead and replace that by partial derivatives with respect to the radius. Okay? Now, what do I know here? Well, I know the potential has to remain finite in every region. There's no uniform field superimposed upon it in this time, so therefore in the interior solution and the exterior solution, is going to be summation B sub L r to the minus L plus 1, PL cosine theta. And I know that any of the terms corresponding to r to the L terms have to be set to 0 there, because otherwise the solution will blow up as r gets infinitely large. And by similar reasoning, the potential has to be finite as the radius goes to 0. The potential is not going to vanish inside this time around, except at one point. And interior solution is equal to a sub L, or summation L equals 0 to infinity, a sub L, r to the L, PL cosine theta. Now, first condition is that the potential has to be continuous, and this has to hold for all theta. The only way that can happen is if each of these terms is equal to each other. So we have a L r to the radius of the sphere to the nth power is equal to b sub L radius of the sphere to the minus L plus 1. And therefore, a sub L is equal to r to the minus 2L plus 1 times b sub L. So I've eliminated an infinite number of possibilities. Basically, I'm rewriting an infinite number of terms in infinite other terms. And I'm going to apply the condition that the potential, or the electric field, suffers a discontinuity at the surface of the sphere. Now, because the surface charge density is a function of a Legendre polynomial, I can immediately deduce that the only surviving terms from these expansions, or the only surviving term for each one, is going to be the L equals 2 term. So therefore, B greater than is equal to B2 r to the minus 3 P2 and B less than, or B interior solution is equal to a sub 2 r squared P2. And taking the partial derivatives, we wind up with minus 3 b sub 2 over radius of the sphere to the 4th power times P2, second order Legendre polynomial, minus 2a2 times the radius of the sphere times P2 is equal to minus sigma naught over epsilon naught P2. So basically the P2s just drop out as they should. And then also because of this relation between the A coefficients and the B coefficients, this tells me that A2 is equal to B2 over R to the fifth. For your coefficient, b sub 2 is equal to sigma naught over 5 epsilon naught r to the fourth. And A2 is equal to sigma naught over 5 epsilon naught over r. Now, plugging both of these back in to their respective expansions, we wind up for the interior solution is equal to sigma naught 5 epsilon naught r squared over radius of the sphere times P2. Exterior solution equals sigma naught over 5 epsilon naught radius of the sphere to the fourth power over r cubed times P2. So this is, by inspection, continuous across the boundary at the radius of the sphere. And also, you can see that you choose we have the proper limits here. This vanishes at, or remains finite at the center of the sphere. And this remains finite as r approaches infinity. And also, if you were to go ahead and plug this back in, you'd see that you would indeed wind up with minus sigma naught over epsilon naught times the second order of Legendre polynomial. Now, the first example, you were told what the potential was at the surface of the sphere. The boundary condition was that the potential vanishes. The other boundary condition that you were given is that the potential went as, or rather I should say the electric field, was uniform as you got infinitely far away. So that told you that in that case the potential actually did not go to zero as r got very, very large. Rather it went as minus E naught r cosine theta. And using the boundary conditions you can figure out what the surface charge density was. Here the approach is a little bit different because you're told what the surface charge density is, and you've got those same two boundary conditions that have to hold. And in this case you use both of these to determine the interior and the exterior solutions, and you're able to eliminate half the possibilities here because potential has to be finite inside. You can eliminate half the possibilities here because potential has to remain finite as r approaches infinity. So continuity gives you the relation between AL and BL, the coefficients, and the discontinuity in the electric field enables you to get a value for the only surviving coefficients. Okay? Let's leave that up there for a minute, and we will move on. The third problem I'm going to work through, we're going to apply a potential to the surface of a sphere. And this time I'm assuming that the potential is proportional to cosine 2 theta and times V naught. The general order of the potential has the form same as always. Summation L equals 0 to infinity, A sub L times R to the L, plus B sub L R to the minus L plus 1, all times the Lth order Legendre polynomial. So what are my boundary conditions? Well, first off, that the potential is continuous across the boundary. And the second condition is that the normal component of the electric field suffers the discontinuity at the boundary, and that discontinuity is equal to sigma, the surface charge density, over epsilon naught. Now, we don't know what the surface charge density is yet. We can figure that out in the course of analyzing this problem. But the first condition tells me how AL and BL are related to each other. The solutions have to remain finite in the appropriate regions. So in other words, for the interior solution, that has to remain finite as R goes to 0. That eliminates the possibility of having any coefficients or any terms of this form, the second form. So this is equal to summation L equals 0 to infinity of A sub L times R to the L PL cosine theta. Exterior solution must also remain finite, but this time as R approaches infinity. So that eliminates the possibility that you'd have any terms of this kind. So you're just going to have summation L equals 0 to infinity, B sub L R to the minus L plus 1, PL cosine theta. So continuity of the potential will provide you with a relation between the coefficients A sub L and B sub L. These will have to be equal for every term. So in other words, for every L, this has to be equal to this. So hence, continuity condition implies that A sub L is equal to B sub L times the radius of the sphere to the minus 2L plus 1 power. So in other words, we're setting this equal to this for every L. Otherwise, this condition won't be satisfied for all cosine theta, or all theta. Okay, so I've eliminated, already figured out half of what the coefficients are in terms of the other half. Now I want to apply this actual condition, what the potential actually is at the surface of the sphere. Now, my task might be much easier if I can write this in terms of Legendre polynomials and then make use of the orthogonality condition to eliminate basically an infinite number of terms. Let's see, let me write P naught here is equal to 1, P1 is equal to cosine theta, and P2 is equal to 3 cosine squared theta minus 1 over 2. I need to write this in terms of P naught, P1, and P2. Making use of a trigonometric relation, cosine 2 theta is just equal to 2 cosine squared theta minus 1. So now I'm in business. I can write this in terms of these three terms, generally speaking. You want to start from the highest order or highest power of cosine theta and then work your way down. So if I put P2 in here, that's 3 cosine squared theta minus 1 over 2. If I multiply that by 4/3, that'll leave me with 2 cosine squared theta. But that means I also have an additional minus 1/2 times 4/3, or an additional minus 2/3 to deal with. So I add 2/3. So these two terms together equal 2 cosine squared theta. And then, of course, I do have the last one. This is just 4/3 times second order Legendre polynomial. And then over here, 2/3 minus 1, well, that's just the 0th order Legendre polynomial, or minus 1/3 P naught. Because the potential has this form on the surface, that means the only surviving terms from either of these expansions are the 0th order term and the 2nd order term. We have A naught plus A2 R squared times P2. We have B naught over R plus B naught over R cubed P2. Radius of the sphere potential is equal to V naught times four-thirds P2 minus 1/3 P naught. And the interior solution is equal to A naught plus A2 R squared P2. The only way this condition can be satisfied is, I should write P naught here. And I should write P naught here as well, and P naught here as well. That's just equal to 1 in any case. And the only way this condition can be satisfied is that this term is equal to this term, and this term is equal to this term. So in other words, A naught is equal to minus V naught over 3, and A2 is equal to 4/3 V naught over R squared. Now, I could apply this continuity condition and solve for B naught in terms of, or B's in terms of A's, or I could just apply this condition directly. It really makes no difference. Answers. Now you solve for the only two non-vanishing coefficients from each expansion, and you solve the problem. find your solution, and the interior solution is equal to minus V naught over 3 plus the 4/3 V naught R, little radius of the observation, or the observation point over the radius of the sphere squared times P2. Exterior solution is equal to minus V naught over 3 radius of the sphere over little r plus 4/3 V naught radius of the sphere over little r quantity cubed times P2. Notice I've left out the P naughts because that's just equal to 1 in any case. So clearly this is continuous at the boundary, and it also has satisfies the appropriate boundary condition that the potential is equal to V naught cosine 2 theta. Okay, so the last order of business now is to figure out what is the surface charge density here, and I will have to erase some of this to give myself a little bit more room, so I'll just leave this up here for another minute. And then we'll move on. This is your boundary condition that the electric field, or the normal component of the electric field, suffers a discontinuity at the surface of the sphere, and remember, electric field is equal to minus the gradient of the potential, which is why we have the minus signs reversed here. And again, the normal component is in the radial direction, so that's why we're taking the partial derivative with respect to r. So first case, we've got the partial derivative with respect to r, so this is V naught over 3 r squared. Have a minus and a minus, and over here, actually you have minus, 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 so we'll have 1 and a minus. And then over here we'll have plus 4 V naught over 3 r cubed, and it's times 3 as well, r to the 4th. And then for the interior solution, that first term vanishes. You take the partial derivative with respect to r here. That just gives 0. Second term, and I don't want to leave off the P2s here. And there's your solution. For the surface charge density. So let me make sure I didn't lose track of any minus signs here. that's your answer. Again, if you can write the boundary condition in terms of Legendre polynomial and then just recognize that the only surviving terms are going to also be a linear combination of those Legendre polynomials, and your task is made much more easy. The last problem we're going to work through, you're not going to have that kind of simplification. You will wind up with an infinite series, so let's get straight to that. The fourth and final problem I'm going to work through is that of where you have two hemispheres, the top one of which is at V0 and the bottom one of which is at minus V0. In this case, I'm just going to seek the exterior solution. Now, I could find the interior solution if I wanted to, but it turns out this is a little bit of a longer problem, so I'm just going to do the exterior one. If you want, you can work it out yourself. So what are my boundary conditions? Well, the potential is equal to V0 on the upper hemisphere and minus V0 on the lower hemisphere. Since we are interested in the exterior solution, that means that your potential is going to have this form. It's summation L equals 0 to infinity, B sub L R to the minus L plus 1 PL cosine theta. Notice I've discarded the AL terms because I know my solution has to remain finite, and any kind of R to the L term would blow up as R approaches infinity. Here, unfortunately, I'm not going to wind up with just a simple expression. I will wind up with a series with an infinite number of terms in it. So, I'm going to have to go through and multiply through by some PL prime sine theta, integrate from 0 to pi, and that's going to give me 2L L prime over 2L plus 1. On the left-hand side, it goes 0 to pi, BR theta, PL prime, sine theta, d theta. Over the right-hand side, and this, by the way, is at the surface of the sphere. And notice I've left out the arguments of the Legendre polynomials, basically just to save myself a little bit of space. So on the right-hand side, I do have the integral, and I can make use of that orthogonality condition, which has the effect of picking out one specific term. So that is going to be B sub L R to the minus L plus 1 times 2 times the Kronecker delta L L prime over 2L plus 1. And so therefore, this right-hand side just becomes BL prime radius of the sphere to the minus L prime plus 1 power times 2 over 2L prime plus 1. So it affects the Kronecker delta, picks out one term, and that's the term where L is equal to L prime. Over on the left-hand side now, unfortunately, the potential does depend on the angle, because from 0 to pi over 2, the potential is equal to V naught. From pi over 2 to pi, it's equal to minus V naught. Okay. Now, we valued the right-hand side readily. Left-hand side is going to take a little bit of work to figure out an answer. And also, since there's L and L prime are just dummy indices, I'm going to go ahead and drop the primes off the L's just to clean things up a little bit. Okay, so how do we proceed? How in the world do you evaluate integral from 0 to pi over 2? Here's where you want to make use of recursion relation. And anytime that you work on these problems, it's always a good idea to have a math physics book on hand or a cheat sheet where you've got the recursion relations listed. We went over those in the first part of this lecture, and the one that's going to be very useful to us right now is that 2L plus 1 is equal, times PL is equal to PL plus 1 derivative minus PL minus 1 derivative. So in other words, this is a way of relating the nth order Legendre polynomial to derivatives. The derivative with respect to cosine theta of the L plus 1 order Legendre polynomial, and the derivative with respect to cosine theta of the L minus 1 order Legendre polynomial. And also, it's convenient here to make a change of variables. So in other words, instead of going from 0 to pi over 2, let's set x equal to cosine theta, and dx is equal to minus sine theta d theta. And I'm also going to flip this, put the unknown coefficients BL over on the left-hand side. So this is good. BL r to the minus L plus 1. And there's a factor of 2 there. Instead of going from 0 to pi over 2, we're going to integrate from 0 to 1. And instead of going from pi over 2 to pi, we're going to go from minus 1 to 0. And again, when you set, if you look at the limits here, x equal, cosine theta, cosine 0 is equal to 1. So that'll be 1 here, and then that would be 0. But then you'll have a minus sign here, so that's why the limits of integration are flipped. And I won't forget my V naughts as well. And here what I've done is I've multiplied both sides through by 2L plus 1, so now I've got 2L plus 1 times this first integral, and 2L plus 1 times the second integral. And then I can make use of that recursion relation. we made a change of variables, x equal to cosine theta. I'm now taking the derivative with respect to x. And so you're taking the integral of first derivative, so that's just the value itself. It's just going to be equal to v naught times PL plus 1 minus PL minus 1, evaluated from 0 to 1. And the second term is PL plus 1 minus PL minus 1, but this time evaluated from minus 1 to 0. I'm going to go ahead and divide both sides through by 2 and r minus L plus 1, so that will give me V naught, or the L plus 1, over 2. Evaluate all of these terms. So again, this is where it comes in useful to have a list of values on hand. So in other words, Legendre polynomial about when the argument is equal to 1, regardless of the order, is always equal to 1. If you happen to have minus 1, that's equal to minus 1 at the end. If you happen to have, and for even orders, evaluated at L equals 0, will vanish. Even orders, and this is where you do need a cheat sheet here. So this is minus 1 to the n. Two n minus 1 double factorial over 2n double factorial. Now, if you never use a double factorial, basically it's the same thing as a factorial, except that you're only counting the odd numbers. So in other words, you would go at 7, 5, 3, 1. Okay, that's what you'd have for an odd double factorial. For an even double factorial, it would go as 8, 6, 4, 2. So it works the same way. It's just that you're counting the odd ones here, and for even, you're counting the even numbers. So anyway, the point of it is that the for odd orders of Legendre polynomials evaluated at 0, those are equal to 0. For odd or even powers of Legendre polynomial evaluated at 0 is a more complicated expression. It's minus 1 to the n times double factorial of 2n minus 1 all over double factorial of 2n. Now, how do you figure that out? Well, with these cases, you can see that by inspection and just by reasoning, by inductive reasoning, you can see that applies for all cases. Likewise, for the odd Legendre polynomials, you can see that that's going to be 0. There's a way to prove it rigorously, and that's what you want to handle in your, or what you should handle in your math physics class. This one, you can do that by doing a binomial expansion of the generating function. Again, I don't want to get into proving it, I'm just making use of it. And if you want to prove it, do consult textbook either by Mary Boas or by George Arkin. Okay, so that being said, I'm going to plug this into here, okay? So what does that tell me? That tells me that these two terms are both going to be 1, right? Because after all, any order of the Legendre polynomial evaluated at 1 is equal to 1. So I have 1 minus 1. Those drop out. Now, what about the minus 1 terms? Well, it tells me it's minus 1 to the n. However, if this is odd, L plus 1's odd, then L minus 1's odd. So these are going to have the same sign. You're taking the difference of those two. That's going to be 0. And likewise, if L plus 1 happens to be an even number, and L minus 1 is an even number, you'd wind up with 1 minus 1. So they'll cancel out in any case. Now we'll just have these two terms, and you'll in fact have minus PL plus 1 evaluated at 0, minus PL plus 1 evaluated at 0, plus PL minus 1 evaluated at 0, and PL minus 1 evaluated at 0. So you've got each of these is going to have a factor of 2, leading to cancel out with this 2 in the denominator. So I need to evaluate this, okay? So if L plus 1 is odd, which would mean L minus 1 is odd, those will vanish. So the only way this will be non-zero is if L plus 1 is an even number. So let's say I let L minus 1 equal 2n, and L plus 1 equal to 2n plus 2. After all, they're just dummy indices. So therefore, this means my coefficients only going to have non-zero contribution from the odd coefficient, so in other words, when L is equal to 2n plus 1. And I'll have V naught times the radius of the sphere to the 2n plus 2 power. And on the right-hand side, I will be left with minus p, 2n plus 2 order, evaluated at 0, plus p, 2n order, evaluated at 0 as well. And I'm running out of room here, so I'm going to go ahead and erase this part of the board. Substituting in for Legendre polynomial evaluated at 0, in the first case, it's going to give us minus 1. Or minus, rather. Minus 1 n plus 1. N plus 1 double factorial over 2n plus 2 double factorial. Second term gives me minus 1 to the n times 2n minus 1 double factorial over 2n factorial. I'll factor out minus 1 to the n. After all, we have minus 1 to the n plus 1, so that's the same thing, that's minus 1 to the n. And then I'm also going to factor out a 2n minus 1 double factorial over 2n plus 2 double factorial. So the first term, I'm pulling out the 2n plus 2 double factorial in the denominator, so that's taken care of. However, in the numerator, that's going to leave a 2n plus 1 term here, right? Remember what I just said about double factorials. If you have 7 double factorial, that's just equal to 7.5 times 3. 8 double factorial is equal to 8 times 6 times 4 times 2. Okay, so in other words, when I pull out the 2n minus 1 double factorial, it's going to, from this, it means we're going to be left with 2n plus 1. Over in this term, the 2n minus 1 double factorial is taken care of in the numerator, but I'm pulling out a 2n plus 2 double factorial from the denominator, so that means that leaves over a 2n plus 2 in the numerator. So I add everything. Plugging in these coefficients into your solution and remembering that we had to make the change of variables from L, or change of indices, I should say, from L equal to n, 2n plus 1. And there's your solution. This is equal to V naught summation n equals 0 to infinity minus 1 to the n, 2n minus 1 double factorial over 2n plus 2 double factorial for n plus 3 times the radius of the sphere over the radius of observation, 2n plus to the 2n plus 2 power. Again, you're making substitution. L is equal to 2n plus 1. So this is why r, little r has value minus 1 over r to the 2n plus 2 power. And then your Legendre polynomial is p 2n plus 1 cosine theta. And that is the conclusion of this problem. I will leave this up on the board for a few minutes. And truth be told, this is really a graduate level problem, not undergraduate, but I think it's instructive nonetheless at this stage. So if you want to do the interior solution, your expansion would be of the form summation L equals 0 to infinity, a sub L, r to the L, PL cosine theta, and just follow the same procedure as I did. Okay, so that concludes today's lecture.